Good day and welcome back to the fourth part of our discussion on enclosed areas. In this part of our discussion, we are going to take the ideas developed in the previous videos and generalize to finding the area enclosed under the graph of a function given by y equals f of x as x varies from a to b, where once again we're supposing that the graph is entirely positive. And the idea or approach we have is identical to our setup from earlier. The area is going to be equal to the limit as n approaches infinity of r sub n, where r sub n is what we refer to as being the right-hand approximation of the area under this curve using n approximating rectangles with the height determined at the right-hand endpoint. So to start off with, what we need to do is take the interval from a to b and break it up into n equally spaced subintervals. So our first step is we break this interval ab into n equally spaced subintervals. And we know exactly what the width or the length of each of these subintervals will be. It's what we previously referred to as delta x, and it will be the length of the entire interval, b minus a, divided by the number of intervals we wish to break it up into. So b minus a over n. And I'm going to go ahead and draw a separate number line just to assist us. So we have a to b, and we're breaking it up into n equally spaced subintervals. And notationally, we will let a be equal to x sub 0, then x1, x2, x3, all the way to b equals xn. And then somewhere here in the middle, we have a general interval. And I'll say x sub I minus 1 to x sub I. And notationally, how I want to think of this is x sub I represents the right-hand endpoint of the ith subinterval. And immediately that gives us a formula that we can use as well. We start off at a, and to get to x sub I, we must travel across I of these subintervals. So that would be a plus I delta x. And two key formulas that we are going to need are delta x and x sub I. And what we would like to do is think of each one of these subintervals as being the base of a rectangle. And just to remind you graphically, we've taken our interval from a to b, and we've broken it up into all of these subintervals. And then on each subinterval, we are going to approximate the area enclosed under the curve by forming a rectangle where the height is determined by substituting the right-hand endpoint of the interval into the function. We add up the areas of those rectangles, and we get an approximation to the area enclosed underneath the curve. So with that in mind, let's write down a formula representing r sub n. Working from left to right, the length of the base of the first rectangle and all of the rectangles is delta x. The height of the first rectangle is determined by substituting x sub 1 into the function. So we're thinking that this formula delta x is a base, f of x1 is a height. And then we keep doing this as we work our way across. For the second rectangle, its base is delta x, its height is determined by substituting x2 into the function. And then the third rectangle, and we do this all the way across to the nth rectangle. So we're just adding up the areas of these rectangles. And note there's a nice pattern. We can express this in sigma notation, just like we did in our previous example. Note each and every term involves a delta x, and what else it involves has this pattern f sub x sub I, where we start off with I equals 1 and we continue adding until we get to I equals n. And we are now ready to write down a general formula that represents the area enclosed underneath the curve. And we do so by taking the limit as n approaches infinity. So in general, the area of the region that lies underneath a continuous function, that is an important assumption, and above the x-axis from x equals a to x equals b is given by the following formula. That area is equal to the limit as n approaches infinity of r sub n, which from above is the limit as n approaches infinity of the sum from I equals 1 to n of f of x sub I delta x. But of course, in order to be as precise as possible, we need to define each of these quantities. Delta x is b minus a over n, and x sub I is a plus I delta x. And this now gives us everything that we need to find the area enclosed between a curve and the x-axis. What we will do in our next video is investigate one additional example before moving on to the next topic. So stay tuned and take care.